Yes, dear friends, now we have gone one more step and we have seen for a mass spring damper system of second order in nature, how do I analyze what is the mathematical background or trick or technique required to find out the damping ratio and natural frequency. It is more important to make our understanding very clear that a second order system need not oscillate. It will oscillate or it will come to a return without oscillation. That depends upon what is the value of C, right? That is the damping constant. Okay. Or in terms of zeta, if I tell, if the damping ratio is less than 1, it will be oscillated return. If it is zeta greater than 1, it will be over damped case, no oscillation, and zeta equal to, or damping ratio equal to zeta critical, or damping ratio equal to 1, then it will also not have oscillation. It will come back and the return will be fastest. All those things you need to analyze before you apply all this trick, right? Don't do it blindly. But preparing ourselves with this sort of a trick and skill, we need to see how to put our first foot forward to analyze an aircraft dynamics. We will not rush. We will take a simple case. We will take a case where, say this is the wind tunnel, and I have mounted aircraft. This is the elevator. And I mounted in such a way that I have mounted in such a way about the hinge point such that it has only pitch degree of freedom. It can only do pitching. No motion like this, right? Only pitching, right? No plunging motion, only pitching motion, right? No yawing motion, no lateral motion, only pitching motion is permitted. I want to analyze this. What I do, I give it a small disturbance. I give some elevator input, delta E, and then release it. So I like to study how this oscillation will happen and how its transient will behave. And I would like to use whatever we have understood for a mass spring damper system. Can I use those things directly or not? And when you are using it, what more understanding is required, which will make our life easier to transform the knowledge of a mass spring damper system to an aircraft system, right? Remember, for a mass spring damper system, we are talking about Ft and we are talking about motion, linear motion along x direction, this motion. But here the difference is it is an angular motion, right? So whatever this forcing function was doing as a member of force, here that force is replaced by the moment. What type of moment? It is the, what is this moment called? Moment about y-axis. This is pitching, so this is called pitching moment, right? And if you recall, this pitching moment will be function of alpha, angle of attack. You know what is angle of attack? Angle of attack is the angle between the chord line and the velocity vector, right? Then it will be function of q, that is the pitch rate. What pitch rate it is oscillating, function of alpha dot, and I am putting a delta E. We have done all this thing in our last course. Alpha dot, because you know there is a delay in the downwash, right? So whatever time you are analyzing, actually those downwash has not happened because it takes finite time for the shedding vortices to travel to the tail. So there is a delay. And on a quasi-steady approach, we try to approximate moment through its non-dimensional term. This is f alpha. For q, you used to write q c by 2v. Why? because we want to keep this all argument in non-dimensional form. You see alpha is in radian, non-dimensional, q is in radian per second, so it's a dimension. So we have changed this q to qc by 2v to make it non-dimensional. Similarly, alpha dot also we will do like that, which all these things you are familiar, and those who need more clarification may follow my last lecture on aircraft stability. If this is the form, then using a Taylor series and assuming a linear aerodynamics, I can write Cm, expand Cm as Cm naught plus Cm alpha into alpha plus Cmq into Qc by 2v plus Cm alpha dot into alpha dot c by 2v plus Cm delta E into delta E. What is Cm alpha? This is dCm by d alpha. What is Cmq? Cmq was dCm by dq c by 2v. Similarly, Cm alpha dot is dCm by d alpha dot c by 2v. Similarly, Cm delta E. These are the partial derivatives. What is the meaning of Cm alpha? Is the change in Cm per unit change in alpha holding other variable constant. Right? So this is a partial derivative. Let us take a simplified case where I put Cm not equal to 0, then Cm will be equal to Cm alpha into alpha plus Cmq into Qc by 2v plus Cm alpha dot into alpha dot c by 2v plus Cm delta E into delta E. Once I put Cm not equal to 0, come back here. If my wing is symmetrical, tail is symmetrical, the body is fuselage is symmetrical, everything is symmetrical, so then naturally at alpha equal to 0, there will not be any Cm. So I can always put Cm not equal to 0. Now come back. When we were doing mass spring damper system, our first step was to write the equation of motion. That is how we wrote x double dot equal to this, or x double dot plus c by m x dot plus k by m x equal to f of t by m. That was the equation of motion. But here also you have to write equation of motion, but we understand this is now angular motion. Okay? So that will be governed by m equal to Iyy theta double dot, or I write it Iyy q dot. Please understand what is theta. Theta is the pitch angle. Theta is the pitch angle. Just to make you more comfortable, suppose this is the airplane, and this is the chord line. This is the velocity vector, and this is the horizontal. Then angle between velocity vector and chord line is actually alpha. And how much this chord line is making with horizontal is theta. And how much the velocity vector is making with horizontal is gamma. Repeat, angle between chord line and the velocity vector is alpha. Angle between horizontal and the chord line is theta, that is pitch angle. And angle between velocity vector and horizontal is gamma. Right? Flight path angle. We are talking about theta pitch angle. That is, if this is the airplane, this is the horizontal, this angle. What is the pitch angle? How much angle it is? Attitude is changing. That is the pitch angle. And the rate with which it is changing, which is theta dot, which is q, and the acceleration is theta double dot or q dot, angular acceleration. Right? So this is typical moment equal to I into alpha, angular acceleration. So I am writing m equal to Iyy q dot. I am trying to develop the equation of motion because I know if I want to solve it like spring mass damper system, my first approach should be to write the equation of motion. So what do I do now? I write Iyy q dot equal to moment. Moment will be what? Half rho v square S C into Cm. For Cm I write Cm alpha into alpha plus Cmq into Qc by 2v plus Cm alpha dot into alpha dot C by 2v plus Cm delta E into delta E. Correct? This is the moment. Moment is nothing but half rho v square x is Cm. If you remember, moment, how do I write? It is half rho v square s c bar into Cm. That is by definition. For Cm, I am using this expression. Right? And why I am doing all this thing? I have to write the equation of motion. And the equation of motion here is regarding the angular motion. So now I can write q dot equal to half rho v square s c bar by Iyy. Iyy is the moment of inertia about the y-axis, right? Into Cm alpha into alpha plus Cmq into Qc by 2v plus Cm alpha dot into alpha dot C by 2v plus Cm delta E into delta E. Now let me write in a neater form so that there are no confusion. Do not forget, we are developing equation of motion, angular motion, and try to see how best we can use whatever we have understood through mass spring damper system. So I write q dot equal to m alpha into alpha plus m q into q plus m alpha dot into alpha dot plus m delta E into delta E. From here, I can write in this form, then what will be m alpha? You could easily see m alpha would be half rho v square s c bar Cm alpha by Iyy. It's very simple manipulation. Whole of this into Cm alpha is m alpha. Whole of this into Cmq into C by 2b will be mq. Like that, you can always find out. Okay? I'll erase this just for your understanding. I wrote this. Now you know that in a wind tunnel experiment, when I am drawing it like this is the wind tunnel, this is the body or airplane, and the velocity vector remain unchanged. It is governed by the pressure ratio. So what is happening? In a wind tunnel scenario, when the airplane is not supposed to plunge like this, only do this, in that case, whatever theta is there, that becomes alpha. Right? Similarly, whatever theta dot equal to q, it becomes alpha dot. And whatever theta double dot equal to q dot, that becomes alpha double dot. This is clear? In a tunnel, in actual practice, what will happen for an airplane? If there is a disturbance, it will not only do this, but also will change the height because there is a lift force. Allowed to move. But here, because it is having only 1 degree of freedom, it will only can do this. So the velocity vector, the gamma flight path angle remains constant. So theta equal to alpha, theta dot equal to q equal to alpha dot, and theta double dot equal to q dot equal to alpha double dot. So I will use it here. So for q dot, I will write alpha double dot equal to m alpha into alpha plus mq into alpha dot plus m alpha dot into alpha dot plus m delta E into delta E. That becomes my modified equation of motion under a wind tunnel approximation, where it assumes the model can only have 1 degree of freedom. It can only do like this, no plunging motion. Right. Now, I will do little manipulation because I want a mass spring damper type equation of motion. So I will write it like this: alpha dot minus mq plus m alpha dot into alpha dot minus m alpha into alpha equal to m delta E into delta E. Okay? You do now see, do you feel delighted? We have conquered our writing skill and we have come exactly same as the second order system. So this is alpha double dot minus mq plus m alpha dot into alpha dot and then plus minus m alpha into alpha equal to m delta E into delta E. For free response, I put this to be 0. The forcing function, which is like f of t, which is here, this is like c, and this is like k. So you can see x double dot plus cx dot plus kx equal to f of t. Exactly same form. Now the problem is solved. So now once we have this sort of equation, how do you find what is zeta and what is omega n? So what you do, you take Laplace transform here, so you get s square alpha of s minus mq plus m alpha dot s alpha of s minus m alpha into alpha of s equal to 0. I've taken Laplace transform on this differential equation. So I've got a characteristic equation now, as we got for mass spring damper system, as s square minus mq plus m alpha dot s minus m alpha equal to 0. This is my characteristic equation. What is our aim? Our aim is to find zeta and omega n. So we'll compare with the standard equation which we have developed already for a second order system, and that is typically like this for a free response. So now I compare what is omega n. Omega n is under root of minus m alpha. And what is zeta? I'll find like this 2 zeta omega n equal to minus mq plus m alpha dot. Right? So if I put omega n value here and 2 goes down, so I can find out zeta. So zeta will be minus mq plus m alpha dot divided by 2 into omega n, and omega n I can use this expression. So how beautifully you see we got the value of natural frequency and the damping ratio using whatever you have learned for a second order mass spring damper system. Apart from the mathematical trick or skill, we also realize one thing, that when I write minus m alpha, and this is under square root, so this becomes a real number only when m alpha is negative. That means this analysis is for statically stable airplane. Please understand, that is why I'm telling you, you need to understand the basics very clearly rather than applying it blindly. Okay? Also here you understand, the zeta primarily depends upon damping derivative mq. And for a mass spring damper system, zeta primarily depend upon c, damping constant c. But here it is, the damping constant equivalent is mq. Correct? And naturally cmq means moment because of rate. So that is the damping characteristics. So it's all consistent, handy. And you see, we'll only be using this understanding when you analyze the dynamic stability of an airplane. Thank you very much.